Right now, as light and sound hit your senses, they trigger a widespread cascade of electrical activity deep inside your brain. In a fraction of a millisecond, raw experience is converted into physical voltage. Memory is a physical, biological structure, a literal rewiring of your cellular hardware that creates a trace known as an engram. When an experience occurs, millions of neurons fire at once. To prevent a total system overload, networks of inhibitory cells spring into action. They act like biological bouncers, suppressing the majority of that activity and forcing a fierce competition for space. This grid illustrates the result of that suppression. The initial wave of activity is rapidly dampened by these thick red inhibitory links. When the surge settles, only a highly specific, sparse ensemble of neurons manages to stay lit. That winning constellation is the engram. A memory is the physical victor of an active biological battle for territory in the brain. To understand how that winning constellation wires itself together, we have to zoom down to a single connection on the receiving end of a neuron, a tiny mushroom-shaped protrusion called a dendritic spine. Embedded in the membrane of this spine is a very specific protein called an NMDA receptor. Its central channel is physically plugged by a magnesium ion that acts like a cork, preventing information from flowing inside. The NMDA receptor functions as a biological coincidence detector. It only ejects that magnesium cork when a chemical signal arrives from the sending neuron at the exact same millisecond that a surging electrical spike fires from the receiving neuron. This simultaneous hit pops the cork, allowing a flood of calcium ions to rush in. That calcium influx triggers a cascade of molecular events that physically expands the dendritic spine and adds new receptors to its surface, making the connection between the cells permanently larger. This simultaneous firing creates a permanent physical bridge between neurons, hardwiring that fraction of a second into the brain's anatomy. We now have the physical trace of a single millisecond. But human experiences unfold over continuous time. Capturing isolated, static flashes isn't enough. The brain must find a way to stitch them together into a coherent story. The hippocampus solves this through the theta rhythm, a continuous wave acting as the brain's internal master clock. Through phase precession, scattered electrical flashes lock their spikes to specific rising and falling edges, forced into an evenly spaced sequence, sorted perfectly into chronological order. Without this biological clock dictating the timing, neurons would fire out of order, turning our memories into a jumbled, confusing mass of sensations. But the clock creates a volume problem. You experience millions of sequenced moments every single day, and the brain lacks the capacity to store them all. It must select which sequences are actually worth keeping. This selection happens in the quiet moments. During brief periods of rest immediately after a significant event, the hippocampus temporarily pauses its normal tracking of the environment. It initiates a sharp wave ripple, a synchronized burst of excitation that sweeps through the neural network, overriding the normal background hum. This ripple is an awake replay. It rapidly fires the exact physical engram sequence of the significant event that just occurred, essentially playing the tape back on extreme fast-forward. This fast-forward replay acts as a biological bookmark. It prioritizes the specific memory so the brain knows exactly what data to save permanently when the body eventually shuts down. Permanent storage requires two distinct structures. Deep inside is the hippocampus, a temporary fast-learning workspace. Surrounding it is the neocortex, the expansive, folded outer layer that serves as your long-term storage warehouse. During sleep, the hippocampus enters an offline mode. It ignores new sensory data and instead scans for the specific neural bookmarks it placed during the waking hours. Once it locates them, it triggers sleep replay. The hippocampus rewinds the day's marked events and plays them back on extreme fast-forward, compressing seconds of experience into dense 100-millisecond bursts of electricity. This diagram shows the necessity of that compression. The sleeping neocortex operates on wide, slow frequency waves. The hippocampus must compress its data into rapid bursts so that the packets perfectly slot into the open, receptive windows of the cortical rhythm. This precise timing allows the memory to be gradually transferred out of the temporary workspace and hardwired directly into the cortical circuits through a process called consolidation. The brain utilizes sleep as a period of high-speed biological data transfer that permanently offloads our experiences to long-term storage. This brings us to a final question. Why does the brain expend such immense biological energy to run this complex saving and sorting system every single night? As these newly consolidated engrams are stored in the neocortex, they physically overlap with older memories. By sharing key intersection points, they link related concepts together to form a comprehensive, complex map of interconnected relationships. This structural database exists to recognize patterns and predict the future, turning past experiences into a predictive engine.